Good afternoon. Good morning, everybody. So today we start our new chapter, chapter 5, magnetostatics. So we're talking about a static situation for the magnetic fields. And we call it statics. You might wonder, we have currents, right? Currents give us produce magnetic field. And currents are charges. If they're moving, they become current. So how is it statics? For electrostatics, yes, we want the charges are in equilibrium. But for magnetostatics, we're talking about a time-independent situation. So as long as the current is steady and is not changing with time, it's a static situation for the B field, right? So until 1800s, magnetism are considered different phenomenon, different distinct force of nature. And they're different from electrostatics. People are looking at them separately, right? For example, we know that the magnetic phenomena are different from electric because magnets do not attract or repel charges. And unlike the static charges sometimes fade away, they dissipate easily, but magnets don't fade away. So we know that they have different features. And in fact, but people have been studying the magnetic phenomenon way before they study the electric. For example, back in 1568, Gerardus Mercator pointed out that needles point to terrestrial source. Needles will respond pointing to the Earth. That is many thousands, hundreds of years ago. And in 1800s, William Gilbert has discovered that our Earth is actually a big magnet. This is 40 years before Newton even realized about Earth's gravity. So that's, way earlier. People have been studying the phenomena of magnets. It's not until, so you see that they have been studying this for hundreds of years, and it's not until 1820, Oersted, who is the instructor at the time, was performing a demonstration in his class. So he observed that the currents, so he ran a current through a wire, and at the time there is a compass needle close by. He noticed the compass needle deflects when the current is turned on, just like how a compass needle will respond to a magnet. So that's not until then, it was the first time people start to relate the electric phenomenon with magnetic phenomenon. And obviously he performed that experiment more carefully after he made that discovery in class and had more and wrote about it. So today we're going to explore magnetic fields. We'll start talking about the features of the B field. We'll look at Lorentz force. We'll talk about the sources for the B, just like how we talked about the sources for the E. And eventually continue coming up the next few days. We will talk about Biot-Savart to calculate the B field, and also you can use Ampere's law to calculate B field. Some of this may feel really familiar to you because you have seen it in intro courses, but if not, we'll have a chance to review them, okay? So start with the features for the B. Okay, just 1 second. We can look at how B fields are similar, very similar to the E field, or how they are different. So let's talk about how they are similar. At the same time, they're similar. At the same time, they're also different than B. So as I show in this picture, you probably have guessed, we formed this picture, right? This is really just showing a magnet, a bar magnet. We form such a picture by, you can spread some iron filings those filings around, and they will realign themselves according to the magnetic field. So these lines sort of give us the idea what are the magnetic field lines, right? So they're kind of coming out like this. So if this is the north, the south, kind of start from the north and then go back to the south. So this looks very similar to the E field, like they are a dipole, right? Like a dipole field. But at the same time, they're also different. So how are they different from a dipole field? Anybody would like to talk about how they think this field is different from the dipole field?
There is no electric field lines inside the, I'm sorry, magnetic field lines inside the magnet itself.
Yeah, unlike the dipole is like there's a positive charge and negative charge. Electric field lines start from the positive and end at the negative. They end at the negative. So in generally, the shape looks similar, but the magnetic field lines are closed loop. So it actually continues inside the magnets. Unlike the electric field lines, it ends here and it doesn't continue, right? This one actually goes through. And also it's different from a net magnet in the sense that here you can separate a dipole into two monopoles. But for magnets, you can cut them in half. You can cut this, but you will form a new north and south pole. Right? No matter how much you cut it, you will always end up with a pair, a dipole. So that's also different from a dipole field. We can also look at the difference between B and E field from our Maxwell equations. So as you recall, del dot E is what? Rho over epsilon naught. And that's Gauss's law, right? So this is Gauss's law. This will also indicate that the charge density is the source of E. Okay, and it has a non-zero divergence if you have a non-zero density. Okay. However, divergence of B is equal to what? What is the divergence of B?
0.
0, very good. This is indicating there is no magnetic monopoles. Right, because here we are talking about a non-zero divergence, we mean there is a source, mathematically it's a source or a sink. Looking at the dipole, you have a source of density, right? You have the charge, that's where your field coming from. As we said earlier, here you don't have a single source point or a sink point, right? These field lines are going continuously. So that's different. But we can also find out the parallel law. So the parallel law for electrostatics is actually not the no monopole law. It's actually the curl of B is equivalent to the divergence of E. So the curl of B is equal to, you still remember the right-hand side of this equation? What is the curl of B? The curl of B is mu naught J. J is the charge current density. Okay, so this is telling us that current density J is the source of B. And so this one is which diverge, give you non-zero divergence. This one give you which curls, would give you a non-zero curl. Okay, so this is equivalent to that in the sense that tell us what is the source for the E field and what is the source for the B field in the way that they're different. So these are electrostatics and magnetostatics. So both of these equations are for static situations. Okay. Now mu naught is a constant. It's a permeability constant, 4 pi times 10 to the negative 7 newtons per ampere squared. 1 amp is 1 coulomb per second. So we talked a little bit about the feature of B and how it's similar and different to the E field. And then now let's talk about the force. If you have a charge and the charge is in the electric field, this charge will feel a electric force, static force. Now, if the charge is moving inside a B field, it's also going to feel a force from the magnetic field, which is QV cross B. So in generally, when there is either E or B or maybe both, we can write and add up the forces together to be the Lorentz force acting on a charge in the E or and B field. So we will just write F is Q E plus V cross B. Okay, we'll just write it in generally something like that. This is a force on little charge Q. Okay. Obviously, how do people know its force is this in this particular format? And this is experimental finding. This is from people did experiment and they found out the force on the charge is in this described by this equation. Here, since we are talking about, they all give us the force units, we can talk about the units for the B. Now, the SI unit for B is 1 Tesla. You can derive what is 1 Tesla from using newtons divided by velocity, right? So you have 1 Newton divided by Coulomb, of course, and meters per second. Okay. It turns out this is actually a very big, very big unit. Because 1 Tesla is 10 to the 4th 10,000 Gauss. Now, sometimes people use a different unit to describe the B field. If you use the centimeter grams second unit to describe the B field and use Gauss. So 1 Tesla is 10,000 of Gauss. And okay, how do we know that is large? We can compare with a big magnet that we have, which is the Earth field, is only half a Gauss. So 1 Tesla is a very big unit, right? So in real life, you will see 10 to the negative 6 Tesla or something. It has to be, if you see a big unit of Tesla, you probably know made a mistake somewhere. Likewise, Coulomb is also a very big unit. In real life, we often talk about microcoulombs, nanocoulombs, right? We don't say we have a point charge here that has 2 coulombs. We don't have such a big unit. Even a few coulombs, maybe you were talking about the clouds when it has thunderstorms, but not the stuff that we're dealing with in our lab. Okay, so Tesla is a big unit, and this is the Lorentz force is QE plus V cross B. Okay, so both the E field and B field, if you have both of these fields present, you have to think about the force from both of the sources. And there's something interesting we can see about the force from the magnetic field. Since the F is QV cross B, and you can see that F dot into dl, if you're looking at the work done by this force, right, it will be QV cross B dot into dl. Now the dl will be the displacement, which is velocity times time. So you can see that V cross B is a quantity that is perpendicular to velocity. So you use a vector that's perpendicular to velocity, dot into velocity. Now, these two vectors are perpendicular to each other. So dot product is going to be 0, right? Which indicates that the B field does not do work on individual charges. Because this force is always perpendicular to the displacement. right? This is kind of similar to how if you have a pendulum, right? And this tension and this displacement, you can see no matter where you are, your tension is always perpendicular to your displacement. Similar to that, in the sense this force doesn't do any work. So likewise, if we just look at the math, we know the B field magnetic force doesn't do work on individual charges, right? It doesn't mean that B field is not capable of doing work at all. It just doesn't do work on the individual charge. But precisely because of this feature, there may be a lot of interesting applications we can do using the B field. So today we will look at a couple of applications. The first one is called a cyclotron. The actual device may look like this, okay? And what is really doing, if I have a more sort of a diagram show what we're doing is, you have this charged particle, and in between its electric field. Whenever it passes through the electric field, it's going to be accelerated by the electric field, so it gives some velocity. And once it leaves the gap and enter these half a circle, you have a B field present. So you have a velocity, a charge have some velocity inside a B field. It's going to feel this this magnetic force, and it's going to curl around. Okay, so we'll do a little diagram later. It will curl around and it'll come out into the gap again. So once passed through the gap, it's the E field in this gap. It's going to be accelerated again, and it's going to the B field on the other side, and again it will curl around, right? Because if you have a force that's perpendicular to velocity, this is give you a circular motion. So it's going to curl around, and again it's going to pass through the gap multiple times. So you can see the circle gets bigger and bigger because the radius of the circular motion gets bigger and bigger. So as a result of that is once the charge finally move out, the cyclotron has been already accelerated multiple times, and your particle is being accelerated to the velocity that you want in order to do whatever experiment you need. Right. The advantage of doing this is we saved a lot of space by making the charges go around and around, instead of if you have no B field, you have just to accelerate it, then you need a very, very long path, simply continue to accelerate it in the B field, in the E field. And this way you save a lot of space because you can, every time it passes through the gap, it's going to be accelerated again. All right, so let's look at a little bit more detail, draw some diagram to show what can we get from the cyclotron application. So let's say this is your B field in space. And if the velocity coming in is like this, the F is Q V cross B. Okay, so if you still remember your right-hand rule, let's do our right-hand rule to see which direction is our force. So V is right now pointing up the page. B is into the page. So V cross B, I don't know which way you like to do it. You want to do it this way, or you can do it this way. So V cross B is going to give me a force that's pointing to the left. If I have a positive charge, right, it's a left force to the left. Now, if you have electrons, you're going to reverse direction, but let's assume it's going to be a positive charge. Then force is pointing to the left. So you can see that it's going to give you a circular motion, right? This is like a centripetal force. So we can do our application of Newton's second law, F equals ma. F is provided by QVB. Now this is a cross product, and your V and B are at 90 degrees when the V enters, right? So the cross product becomes QV times B. Okay, so this is QV times B is equal to m times acceleration. Again, it's a centripetal acceleration. So using our knowledge from introphysics, this is going to be V squared over R. So we can calculate how much the radius is. How big is your circular motion? So R is going to be mv over qb. Okay. So this is our radius. You can also calculate the frequency. Frequency is how many cycles you will go through in a second, right? How many rounds do you go in a second, which is 1 over t, the period. Now we can calculate period easily by looking at the circumference, which is 2 pi r over velocity, which is v, right? Okay. So the frequency f is going to be v over 2 pi r, and you just calculated v, right? So what is v? V is q b r over m divided by 2 pi r. So frequency f is equal to qb over 2 pi m. Okay. So that's another thing we can find out for circular motion inside a magnetic field. You can see this frequency is actually independent of your initial velocity. The frequency, how many cycles you go through in a second, only depend on the charge, the B field, and the mass of the particle, right? Independent of your initial velocities. Okay. So you can see here, I enter the B field with a velocity that is purely perpendicular to the B. But it's not always the case. What if you enter the B field with some random angle? So for example, we have this question. A proton with speed v enters a region of uniform magnetic field, but making an angle theta with respect to b. So what would be the path for this proton? Okay. So I'll give you a few minutes to discuss before we bring everyone together to look at this question together. Okay. So I'm going to go ahead and open our breakout rooms. Feel free to take a screenshot before you go into the breakout rooms. Okay, so 10 more seconds. Let's wrap up the vote. All right, so any last minute vote before I close? Okay, I'm going to go ahead and close. Let's take a look at our results. So majority of you chose D, circular motion, perpendicular to the page. And next popular answer is actually tied between A and C, like a helical path, or if it's a circular motion, perpendicular to the page. The difference between C and D is the plane of circle, whether it's perpendicular to B or is it at angle with respect to B. Okay. All right, so let's, again, we know that we can use right-hand rule, right? So velocity is a vector, so we can break up velocity into two components. So you have this component Vy, you have this component Vx. Okay, so let me update my share again. It doesn't seem it is recording what I'm writing. So just one second. Okay, so I break it down into Vx and Vy. So what if the particle only enters with a Vy? You have a Vy perpendicular to B. So let's do our right-hand rule. So in which way would your B force pointing at? So if you do QV cross B, right, QV cross B, which way is your force going to be pointing at? V is up the page, B is to your right. So curl your four fingers around from your V to the B direction, and your thumb pointing in into the page, right? So it's coming in, and it's going to be, it's coming in like, so it's going up the page. So if I'm putting this as my up the page, but it's feeling a force pulling it in, so it's going to be circling around. So it's going to circle around in, right? So it's going to have a circular motion like that, okay? And the plane would be perpendicular to B, this plane. Okay. So if that is only if you have a Vy. Now Vx is not going to be affected by D, right? Because V cross B, Vx is parallel to B, it's not going to feel any force. So do you think this, this proton will continue to move forward? Would it continue to go forward? You still have the Vx, right? Yeah, so the Vy, if it goes circular, if it doesn't have Vx, it will just continue to just do a circular path. But it has a Vx, so it will also want to go forward. So as a result of that, what path would it follow?
Helical path.
Yes, it will be like a helical path, exactly like that. It's circling around at the same time, it also go forward. So it will be A, that is the correct answer. Okay, so we have another application for using the charged particle moving inside a B field. So another application is called mass spectrometer. Is, as you can see, it is for us to help us select particles that has a particular type of mass. Okay, so imagine you have some E field in space, and my E field is pointing up. Also have B field in the space, and let's assume that, let's say we put our B field perpendicular to the page pointing upward, and you can feed this field with a lot of particles. You could have a lot of particles coming in. So they're with this kind of velocity. So inside this E and B field, looking at this particular particle Q, assume it's positive Q, then Q is going to feel a electric force Q times E, That's up, right? And Q is going to feel another force Q V cross B. Again, let's see. V is to the right, B is into the page, V is to the right and into the page. Well, oh, so B is out of the page, sorry. B to the right, B is out of the page. So I have my thumb pointing downward. Okay. So this is QV cross B downward. Okay. So QE and QV cross B in this particular scenario is pointing in opposite directions. You know that if it happens, QE is exactly equal to QV times B. Okay. Then you can see the net force is 0. So the particle is not going to go up or down because these forces cancel, right? So it just so happens if your velocity is exactly E over B happens to be that ratio, then there is no force, no net force on the particle. Okay. So imagine if we have all of these, you have this setup and you feed these E fields and B fields with some incoming particles that has a mixed different type of particles, right? Different velocities. And then you will set up some kind of filter over here. You're gonna set up a filter, right? If the particle is too slow, then QE will dominate. It's going to go up. If your particle is too fast, then V is bigger, then V cross B will dominate. These particles will go down. Only the particles at exactly the speed that you want, which is E over B, balance out, how the forces balance out, they will go through. And you have filtered out these particles that you want. Okay, so these are the particles that with a velocity, I know exactly what the velocity is because I select these velocity for it to come through. Okay, so once it comes through, you can again add some B field to make the particle go around. So you can measure the radius. But once it goes through, again, you set up a B field, it's going to go circular, and you can measure the radius. That's something you can do. So you can see it helps you select a particular type of mass for particles or mass to a charge ratio. How do we do that? If we know, because this radius is something you can measure, right? As we derived earlier, a radius is mv over qb. We just derived this earlier. So v, you know, so we know v. These are the particles that made through. So I control my E field and B field. I know how strong they are, so I know what velocity it is. So that we know the mass. This is we know the radius. We can measure, so we can know what mass it is, right? We can calculate the mass of the particle. So we can able to identify what type of atom we're talking about. So you can identify. A lot of times people are looking at the mass to charge ratio. So if you go to this equation, doing the mass over charge, it's going to be BR over V. Again, it's the same. It gives you a ratio about what is the mass to charge ratio of the particle. Again, you can identify these atoms or particles that you want. Okay, so here I have another picture, basically showing you what I draw. Right, you have these particles coming in. You have E field and B field at the same time, and once it made through, you're gonna make it circle around and make a circular motion inside a magnetic field, and you detect them, and you can calculate the rate. You can measure the radius. You can calculate whatever the mass to charge ratio that you want. Okay, so this is an application called a mass spectrometer. Let's look at a question that's related to this particular problem. So, okay, so here you have a proton is released from rest. It's not like coming in with some velocity it's already accelerated. It's released from rest. inside a E field that's pointing upward, and B field is pointing into the page. Okay, this is what the E and B are. Which of the paths do you think the proton will initially follow? It may not continue to follow that path, but initially, which path do you think is the correct path? Okay, I'll give you again some moment to discuss this, and I'll bring everyone back. Okay, 10 more seconds. All right, seems like I gathered most of the vote. I'm gonna go ahead and close it. So it looks like you are in the majority of agreement for C. Can anybody help us walk through this question? So how do we find out the path of the proton initially?
I thought of it was so since initially it's at rest, velocity would be 0, which means that the force from the magnetic field really wouldn't affect it yet. So it just go in the direction of the E field. And then slowly the B field would start to affect it, which would curve it left.
Oh, okay.
By a
You
move.
speed upward, okay. And then you did V cross B.
Yes.
Okay, very good. And V cross B is going to curl it to the left. Very good, excellent. Thank you so much, Nicholas. Okay, so I see my writing again is not being registered. I will have to update this one more time, sorry. Okay, so that's the velocity it picks up, and V cross B again is going to be to the left, right? So which means it's going to follow this path curling to the left. Very good. So C is correct answer, very good. And also it asks us to think about what happens after a long time. So for the next time we have, I would like to solve this question. We'll do it together. So what happens after a long time? So we want to be able to find the trajectory of such a scenario. So that's just initially. What if you let go for a longer time? Okay. So here it's different from, this is different from a mass spectrometer where you have incoming velocity as perpendicular to your E field. Here you release the Q from rest, which means the incoming velocity or the velocity it picks up initially is going to be in the direction of your E. Okay, so what if you release Q from the rest? What happens after a long time? This is what we're trying to solve. Okay, so let's say I'm gonna set up my coordinates with E as showing the uniform E in the Z direction. I'm gonna call this Z direction. And we have my B. I'm gonna call my B also a uniform B in the X direction. Okay, so you know that the force, there is no force in the X direction, right? Because the force from the E field is going to be in the Z direction. The force from the B field is V cross B, which is going to be in the Y direction. So there is no force in the X direction. And there should be no velocity in the X direction because it's never been accelerated in that direction. So I can write my velocity generally as in 0, Vy, and Vz. It's going to have a component in Y and Z, but no component in X. Okay. So I want to be able to write the motion of equation and solve that differential equation. So how do I do a motion of equation? We always start with Newton's second law, right? So maybe you have done some of this in classical mechanics, but let's do this together. So F equals ma, and acceleration is the derivative of velocity. So it's going to be m a, which is vy dot, vc dot, which is the acceleration, right? And now we have two forces. One is from the E field, Q times E. Again, these are vectors. I'm going to write the 0, 0, E because E is in the Z direction. And you have another vectors coming from QV cross B, that is QV cross B. Now I'm going to work this out and then I'll put it in a similar format. Okay, so how do I do V cross B? Let's do it here. B is in X hat only. V, you have a Vy, you have a Vz, and you cross that onto B is in X hat only. Okay. So which means you have to calculate Vy times B, Y hat cross X hat. plus vz times b z hat cross x hat, right? So what is y hat cross x hat? Y cross x give us,
Negative z hat.
yes, negative z hat. And z cross x going to give us y hat. The way I remember this is I write x, y, z in the order, and I go the order. If you do x cross y, it gives you z. If you give you y cross z, it gives you x. If you do z cross x, it gives you y. Right? In that order, if any of these are flipped, then you get a negative sign. There are more than one way to memorize this. This is just my way of helping you remember. Or you can form the right-hand rule, and you can look at it that way. Okay, so this is my v cross b. Okay, so in terms of writing in the XYZ sort of the parenthesis, this is going to be, so this is just a little extra scratch paper I did. It's going to be Q 0, 0, E plus, there is no force in the X direction, so it's going to be Q. You have the Y, you have 0 in the X, but you have something in the Y, which is B VZ times B, negative VY B in the Z. Okay, so we can combine them, become 0 Q V Z B Q E minus Q V Y B, and that's your force. Okay, simply combine them. All right, and that is equal to M times 0 Vy dot Vz dot. Okay, so you have two equations, one for the y, one for the z. So you can see my first equation would be m times vy dot is equal to q vzb, first equation. Second equation is going to be mvz dot, so this equals this, right? And this equals this. Vz dot is equal to qe minus vyb. Okay. So from the first equation, I take the derivative one more time. I get m vy double dot is equal to q vz dot b. Okay. There is a vz dot. So what I will do is I will plug this into the second equation, and I'll get a second order differential equation for the vy. So let's see what we got. Let's plug it in. We have m times vz dot. Z dot is going to be now m vy double dot over qb. So that's my vz is equal to qe minus qvyb. I'll make this peach to show up. Another one here. Sorry, just finally, I get this up. All right. Okay, we finally have space to work on. Okay, so this is the differential equation I formed. This becomes vy double dot is equal to q squared b. You simply group it together. B minus vyb. Okay, so recall this is in the general format of x dot is equal to a minus bx, right? It's in that format. Now, if you don't want to write all the constants and carry it over, you can call them A and B, where A is q squared b over m squared, and B is q squared b squared over m squared. Okay, so you don't have to write it all over again. Now, the general solution to this, you may want to, so when you come across a situation like this, you will look it up on your math book, or you can look it up online to find a general solution. So the general solution to this is going to be some constant, tilde. I write a tilde because later on I want to be able to use C1. Here I don't want to use C1 again, so I just say, oh, it's a different constant, so it's C1 tilde. Sine of square root of b times t plus C2 tilde cosine square root of b times t. And I'm going to add a constant a over b. All right, so you might wonder, okay, is there any idea somehow we can guess the solution? You could recall in your chapter 3 what we solved. We solved a something like, okay, the double derivative of the x function over x is some constant, right? And that is in the format of, you can write it in the format of the sinusoidal functions. But here, the difference is you have another constant in here. So you can guess, okay, if you have a sinusoidal function and then you plus another constant, maybe you can guess a solution that works. So that also works. As long as we find the solution, you can plug it back in your equation. If it satisfies the equation, you're done. Or you can look it up from different your math sources and find out what the general solution for such a equation is. So we found a general solution. That is for our Vy. Okay, so we call this x because sometimes you want to work with some form we're familiar with, but remember to put it back into the variable that you begin with. So this is our Vy. Here, our Vy is this x is going to be, now I'm going to write constant sine square root of b times t plus C2 cosine square root of b times t plus a over b. Okay, and Vy is dv over dy over dt. So we want to find the trajectory, which means we want to solve for the position, but not the velocity. So once you have the velocity, you take the derivative, you get your position. So Vy is dy over dt. So dy over dt is this entire thing, right? C1 sine of this and C2 cosine of this plus a over b. So, okay, so now doing the y is easy. You take the derivative, now become an integral. Okay, so this becomes, okay, this is still the tilde, I'm sorry. This is still the tilde. But now we found the y becomes a C1. It becomes C1 cosine square root of b. Okay, so because when you take the derivative integral, you become cosine plus C2, and now this becomes a sine plus a over b t plus new constant C3. Excuse me. Okay, so you may wonder there might be a negative sign coming in when you do the integral. That's okay. I can simply absorb it into my constants, so I don't have to worry about that, right? So I have my constant C1, C2 to take care of the negative sign if there are any. Okay, so we can see, okay, a over b derivative becomes a over b times time. Again, whenever you integrate something, you get a constant, so C3. So you have this long equation describing your motion in the y direction, your position in the y direction. So you can plug in, don't forget what b is, right? Square root of b is now qb over m and square root, and okay, a over b, this constant is e over b. Now you can plug it in to get the final solution. Okay, so to be complete, we need the y because we also need the z, right? We have found the equations of motion in the y. Now we need to do the z. The z, let's see, we have two equations. We have the first equation. So Vz is m Vy dot over qb. Okay, so Vz is m Vy dot over qb. That's from our first equation, which is m over qb y double dot, right? So once you find the y, you can plug in your y, you get your vz right away. You just take the derivative, the second derivative with respect to time, right, to get your y double dot. Okay, so we can do that. M over qb. So the double dot becomes negative q squared b squared over m squared. C1 cosine square root of bt plus C2 sine square root of b times t. This entire thing. Okay. And that's, let's group the constants together. Negative qb over m. C1 cosine root bt plus C2 sine root bt. Okay. So that is your VZ, and you probably can already predict what I'm going to do next is this is dz over dt. So I will simply, is all of this, I'll simply integrate everything to get your z position, right? So z is going to be negative C1 sine root bt plus C2 cosine root bt plus C4. Okay, so you might wonder, why do I add a negative sign here, but I didn't do it here? Because here C1 is still undetermined, right? C1 tilde is undetermined. C1 is still totally up to me what I pick. I can ignore any negative sign coming my way and group into my C1. But once I fixed, once I decided, okay, that is my C1, I cannot change that C1 again. So if I'm working with a fixed constant here, then I do have to add a negative sign showing this is a different constant for my Z. Now you cannot write C1 again because now it's really a negative C1, okay? So that's the reason why I ignored any negative signs here, but not here, okay? So we're pretty much done, right? You found your equations of motion. So the trajectory in the Y and in the Z, you still have a bunch of constants which haven't been determined, but that's okay. We do have this example in your textbook, so if you wish to go back to look at it, you could. It's roughly in this 214 pages, example 5.2. So in this case, we call them initial conditions. You find differential equation, you plug in initial conditions, you fix the constants, you find the constants. Previously, when we solve for potentials, we call those our boundary conditions, but they're the same thing. Those are all the conditions you know at specific point. If they're at specific point, we call them boundary conditions, or at specific time, we can call them initial conditions to help you find those constants. The general idea is the same. So in this case, to find those constants, we know that the protons start from, you can call it start from a zero origin, and it also starts at zero velocity. So both position velocity is zero. So you can plug it into Y and Z to find all of these constants. Some more steps, and I give you the final solution. So Y as a function of T is going to be E over, there are going to be some frequencies, angular frequencies here. So eventually you'll get something like this, and if you plot it, you will get a path that looks like this. So you have a Y component, you have a Z component. So the red showing the trajectory is following in the Y. So let me show you on this one, it doesn't animate it. So let me change my screen so I can show you how the path goes. So I'm going to switch over to another screen. So let's look at the trajectory of this proton. This kind of looks like this. This is plotting what we just found, and as in Y and Z path. Okay. cycloid. Okay, so that is a long way to go. I just thought this is kind of interesting. It's related to one of the question that we did. So we did a little bit more. And we have a little more time left. So let's do a little bit more about the charge and current density continuity, but mostly we will do the bulk of this in the next week and next class, okay? All right, so after exploring the Lorentz forms, we want to talk about currents because we just realized like the divergence for the E is rho over epsilon naught. So your density, charge density give you the source for your E field. The currents give you the source for the E field. So we should explore currents. And there are different ways for currents, like we had volume charge density, right? We have surface density, we have linear density. And likewise, we should explore volume current density, surface current density, and quantities like that, okay? So let's recall what is current. So what is a current? You get current when your charges are moving, right? So if I consider some line charge density, and they're moving with velocity v. Okay. Anybody still remember the definition for current? Current is defined as
Lambda times velocity.
T,
I'm sorry, say it again, please.
dq dt.
Yes, dq over dt, the charge per unit time. Very good. Thank you for those of you, Benjamin, Nicholas, and Sebastian. So I is going to be dq over dt, change of a charge over time. Very good. So if you have a change charge over time, you have a current, which makes sense because if all the charges are staying there and not changing with respect to time, then that tells you a static electric situation. Charge is not moving, so you don't have current. But once they start moving, you have a change, you have the current. So I is dt over dt, so we can derive what I is in the scenario like this. So you have some line charge density, lambda, that are moving with velocity v. So you can see that the Q, if I look at sort of a length of d, then the total charge that passed through that chunk of volume, in this case is a length of d, is going to be lambda times d. Okay, and all these charges are moving, so it takes time t for the charges to move from here to here. So d is v times t. Velocity times time is the distance, right? Okay, so if I do current is dq over dt, what do I get? What I get is the lambda vt over dt. Lambda v is independent of time, so it's going to be lambda v. dt over dt, you get 1. So just lambda v. Griffiths have this convention that is calling current a vector. Okay, so that's in Griffiths' book. So current is a vector that is in the direction of the moving of the positive charges. Okay, so the same direction as velocity if your charge is positive. So this is in Griffiths call current a vector. Not everyone does this. Other people consider current as in a scalar. So when they're doing, if they need to do an I crossing to another quantity, they take the vector sign and usually put it on L. Okay, so instead of putting the I, vector on I, they put it on L. So L would be the direction of the length, the L would be in which way the current is moving. Okay, so either you can look at current as a vector or not. Our textbook look at it as a vector. Okay, so if you have positive charges, obviously these positive charges moving in this way, you have current moving that way. Now, if you have a negative charge, okay, so if the negative charge is moving this way, then the current is moving to the left, okay? So if you want a current moving to the right, it's either the positive charge is moving to the right or negative charge is moving to the left. That gives you a current pointing to the right. Okay, opposite signs will reverse your direction for your current. So a lot of times you see that, okay, if we're talking about some kind of materials, then you can see you have different charge density, right? Different materials give you different charge density. So if you have this wire has this feature that is N, L, N number of charge carriers per length. Each of the carriers carry a charge Q. Okay, so you can see my lambda can be rewritten using NL times Q, right? Because N is number per length. Each of the number have a charge Q. So the total charge will be N times Q, and it's also per unit length. So that gives us a line density unit. So it's Coulomb per meter, right? So lambda becomes NL times Q. So current I becomes lambda V is going to be NLQV. So this one is something you see quite a bit. You probably have seen it already in 1520. So current is NL times Q times V. Okay. So this is my current. Again, if I treat it as a vector, I will put a vector sign on I and V. Okay. So sometimes your current is not simply moving in one dimension. You don't have just a line charge, right? Most of the time we're dealing with current running across a cross section. So what if current is moving across a cross section? Move through a volume. Not just along the lines as we see there. Okay, so you have these charges, they are moving through a volume. This volume may have some cross section of A, of the A, right? So how do we find the current here? Okay, so we have this question. You have a current flowing down a wire with length L and has a square cross section of a side A. If it is uniformly distributed over the entire wire area, what is the magnitude of the volume current density? Okay. So we pretty much don't have much time left. So I'm gonna let you vote on this. We don't have time to go discuss. You probably still remember this from info course. Or if not, you can think what should we define the volume density be for J, okay? All right, any last minute votes? 5 more seconds. Okay, let's take a look at this together. I'm going to go ahead and end. All right, I'm glad that a lot of you still remember what is the definition for a volume density, right? Volume density J. anyone actually looking at this and thinking maybe my answer is really not there, that I really wanted to have volume density as J is current over volume. But I did not give that option, so that probably narrowed it down quite a bit. So how come we don't use current divided by volume to find the volume density? Just like we did with the volume charge, right? Volume charge density. Why do we divide it by area? In this case, my area is a cross section that is a area of a square, so that's A squared. A is correct, very good. So, but anybody can tell me why, if we have a sort of answer that is I over A squared times A as in the volume, then we choose that, why not that?
Does it have something to do with being perpendicular to the velocity? Or perpendicular to one of the other fields?
You're right, when we do the area, we always look for the cross section. So we always look at the perpendicular area that is perpendicular to your flow of the current, you're right. But why the area? Why not the volume? If we do a current over volume, do we get something meaningful?
No, because that would be like more dimensions than 3, like I feel like.
Yes, very good. That would not be meaningful because your current is already moving in one dimension. So it's not like the individual charges are one single point. You can divide it by the volume. The current already sort of takes, the fact that it is a current meaning it's already flowing in one dimension. So you can only divide it by a area. So I can only divide it by cross section. So A is correct, very good. So current density J is defined as DI over the area. Okay, we will continue to talk more about it in our next class. All right, so that's all for today. If I don't see you at office hours, I'll see you on Friday in our recitation. All right, have a good rest of the week.
You too, Dr. Ryan.
Thank you, Dr. Ryan. Have a nice day.
Have a good day.
Thank you.
Bye.